All right, we're going to pick up where we left off last time in section 6.1, the set of rational numbers. And we had just talked about the fundamental theorem, or fundamental law of fractions and simplest form. And we are going to move on into example number 2, which is writing equivalent fractions. So if over here, the fundamental law says that we are able to multiply the numerator and denominator by a value, this is not a suitable solution for me. This does not look like a bar stool kind of thing to you, does it? Yeah, we're going to have to work on that. Okay, so if we can multiply the numerator and the denominator by any non-zero integer, that's what we're going to do for this one, okay? So we're going to take 7 over 14, and I want everybody to write down 1 or 2 or 3, write down a few that are equivalent to 7 over negative 14. And then I'm going to take some answers, and we're going to make sure that we're all on the same track. Okay, so write down a few of them. Somebody tell me one of them that you wrote down. Anyone? 1 over negative 2. So what did you do to the numerator and denominator to get that? Yeah, so the fundamental principle over here talks about multiplying. Division works too because division is really just multiplying by fractions. And fractions are rational numbers, so we're multiplying by the fraction 1/2. So if you 1/7. So if you multiply by the fraction 1/7 on the top and 1/7 on the bottom, you would equivalently get 1 over negative 2. I think it probably makes more sense or is easier to think about it as being that it works for multiplication and division than to worry about the fractions in this particular context. But what's another fraction that you have that's equal to 7 over negative 14? What do you have, Brooke?
21 over negative 42.
Okay, and how did you get that?
By
Multiplying by 3. Yeah, so multiply the 7 by 3, multiply the 14 by 3. Fabulous. What's another one? Somebody give me one more. Emily, you look like you want to tell me one. 14 over what? Okay, and how did you get that one? Yeah, multiplied the numerator and the denominator by 2. So what about this one? Kind of feels like cheating, right? But it isn't. What did I really multiply by? Negative 1. And negative 1's an integer, so I can use that one actually as an equivalent fraction as well. All right, let's take a look at example 3. Example 3 sort of begs us to do something that's not appropriate. Any idea what it's begging you to do that maybe you're not sure if you can do? Can't hear you, I'm sorry. Really loud. Was that you, Emily? No. It's begging you to take a square root or to eliminate the squares. Doesn't it sort of feel like it? It does. We cancel everything else. Can't we just cancel that too? And of course the answer is no. So let's take a look at what you would want to do instead. So what we would want to do instead is to take the 42 and to take the 35 and to factor those. So what is 42 if we factor it? Yep, 7 and 6. So in the top of this, we really have 7 times 6 squared. And what is 35 if we factor it? 7 and 5. Okay, is everybody good so far? All I've done is replace the composite number with its factorization. So a property of exponents, we'll talk more about properties of exponents. I don't think it's today, I think it's in a couple of lessons. But one of the properties of exponents says that we can actually distribute that 2 to each to the power, to be a power of each of the numbers inside. So we can write this as 7 squared and 6 squared. Or if you want, you can write it as 7 times 7 times 6 times 6. Either of those, not 66, 6 times 6. And you can do the same thing for the denominator, 7 squared times 5 squared. Or if you prefer, you can write it as 7 times 7 times 5 times 5. All right, because what the fundamental law actually said we can do is reduce using multiplication and division, and square roots are not one of those things. They're a multiplication factor, but not by the same value. So what we are allowed to eliminate then from here would be the matching pairs. So the 7 squareds. Or if you did it over here, the 7 and the 7 with the 7 and the 7. That's what you're allowed to eliminate. So what does that leave you with on top? 36, 6 squared, which is 36. And what about on bottom? 5 squared, which is 25. 36 and 25, or 6 squared and 5 squared, don't have any factorizations in common. I mean, I can break 6 down into 2 and 3, but I can't break 5 down into anything that will simplify, so it doesn't help me any. Okay? Any questions on that one? Okay, wonderful fact that you've probably seen before, but maybe not, is that if two fractions are actually equal, that will happen if and only if you're able to sort of cross multiply here and get the same thing. Raise your hand if that sounds like something you have seen before. Okay, sometimes see it, sometimes we don't. So this is one of 4 ways that I'm going to show you to check and see if fractions are equivalent. Okay, this is a really nice way. It's very straightforward. You're just doing a couple of multiplication steps. Feel free to grab your calculator out if you haven't already gotten that. And we're going to take a look at 4 ways of finding out if the fractions 3 over negative 12 and negative 36 over 144 are equal. So we'll do the first one that we just saw, which is the method of Theorem 6.2. So if we're checking to see if these are equal, I have 3 over negative 12. And the question is, does it equal, and if the negative's in front, we're just going to put it on the top, negative 36 over 144. So this method said what I should be able to do is to multiply 3 times 144. What do I get if I do that? 432 is correct. And then also to multiply, negative 12 times negative 36. And it's 432 as well. And so since those 2 numbers are equal, the original fractions were 2. Okay, so that's one way. It's a really nice way. There's several other ways though. So let me show you another option. Option number 2 is that we could actually simplify and compare. Now, it probably is worth noting that they're both negative, so the negatives are really kind of irrelevant in terms of comparing. We've compared. They're both negative, so that's sort of in our favor. Actually, if it were one of them positive, one of them negative, we'd be done at the beginning because we know it's wrong, right? That'd be better. But they're negative, so we already know that those compare and work out okay. The first one we have is 3 over negative 14. Not negative 14, negative 12. In the wrong place. Can I reduce 3 and 12? Yes. What do they both divide by? Yep, they both divide by 3. So I can reduce that. That would give me 1 over 4, and it's negative. So that is reduced form for 3 over 12, negative 3 over 12. The other one is a little bit bigger numbers. I have 36 over 144. Now, no cheating. Y'all know it's supposed to be 1/4 because we already did this problem once, right? So it's going to become 1/4. But look at it as though you didn't already know that. What number would you look at and say, hey, I know both of those are divisible by something? You might try 12. You might try 2. I don't know. You guys said 12, so let's try 12. It's a reasonable assertion because we do learn our multiplication tables up to 12s these days. That's the popular way that that seems to go. So if I did that, this is negative in front. What is 36 divided by 12? Yep, it's 3. And then what's 144 divided by 12? It's 12. And then when you get to this point, you realize, well, number 1, you might realize that's another number I started with in the other fraction. That won't always happen. But at the very least, you should recognize it can be divided further, right? So we just keep going until it can't be divided further. And in this case, we would get negative 1/4 again. So once we get to this point where these match, again, we're done. They're equal. Or if we got to a point where they didn't match, but they were both simplified, we'd be done, and they'd be not equal. Option number 3. Option number 3 are common denominators. So CD, common denominator. The simplest common denominator to find, in the sense of you don't have to look hard, is to simply multiply the denominators by one another. So here's the 3 over negative, I keep saying 14, 3 over negative 12, and the 36 over 144. So the easiest in terms of finding is to multiply the 12 by 144, but if you do it to the denominator, you have to do it to the numerator, and to multiply the 144 by 12. And if you do it to the denominator, you have to do it to the numerator. So those denominators are going to match, which was the whole point. What does that denominator become? Do you have it?
1,700.
Yeah, 1,728. That's right. Okay, numerators. What's 3 times 144? 432. And what's 36 times 12? Hopefully it's 432. Yeah, did it work out? Again, we get to this point, they're equal. So the original fractions were equal as well. Option number 4. Instead of finding a common denominator, we could find a least common denominator. Now, sometimes that's messy to do. I mean, it's not always super nice and neat. On this one, it's pretty nice to do. All I need to do is to compare the denominators I already have, 12 and 144. And what do I need to do to get them to be equal and as small as possible? I need to multiply something somewhere. Okay, let me try the question a different way. What do I need to multiply 12 by to get 144? 12. So if I multiply this 12 by 144, it will look just like the other fraction on the denominator already, right? Okay, not all factorizations work that way. It's a very special case, right? But when it does work that way, it's very nice, and so we're going to utilize it. So if I take my 3 over negative 12, and I multiply this by 12, top and bottom, so that I get 36 over negative 144. And then on the other one, it's already 36 over 144 with the negative in front, because it already had the same denominator as that. Then these two being equal makes the fractions equal. So I don't care which of those 4 methods you use. It doesn't matter to me the slightest. I think probably the first one is the simplest to compute. It's the quickest, easiest number of steps. But I don't think it does a very good job of sort of justifying why it really works. Why are they really equal? So y'all know you're going to have those kids sometimes who are going to be like, why? Why does that work? I have an intermediate algebra class, and we were doing something with fractions this morning, and nobody else in the class cared. They just wanted my shortcut method, which is fine. But she was like, I don't understand. Why is that working? And I was like, can you hang on after class for a second? I'd be happy to show you. So knowing why, whether you remember it on the spot or not, is really good, because then those kids can be serviced well by you when you come back later and say, I remembered why, I looked it up, I learned it before, and I'd forgotten, but here's the deal. Okay? All right, cool fact. This is wonderful. It allows us to check if things are equal, but it actually goes beyond that. If we do our cross multiplication, we can actually also tell which one's bigger than another one if they're not equal, by cross multiplying. So if I cross multiply, I get AD. On the other side, I get BC. And you can see that the directions of the inequalities have to match. So not only can you check for equality, you can also check for which one's bigger or smaller if they're not equal. So let's do an example of one of those. The problem with this question, however, is that there are 3 values, and this does not help you with the 3 values. So you could test them 2 by 2, and that's okay, but you have to be really careful because you could end up testing 2 and one of them's bigger and then have to test it with the third and figure out still which ordering it is. So generally speaking, while this is wonderful if you have, whoops, that's my blank screen. This is wonderful if you only have 2 fractions. It's really not so friendly if you have 3. But other methods are friendly, like finding denominators that match. Can anybody look and tell me by those 3 denominators, what denominator would be nice to turn them all into? A friendly one? 5 won't work because I can't reduce the 13 with the 20 to get the 20 to become 5. But 20 would, right? Instead of making them smaller, I can make them all the denominators bigger, and it would work. So this one's already got a denominator of 20, so I'm sort of done with him. What would I need to do to the 3 and the 5 to make that denominator become 20? Yeah, I would need to multiply by 4 on top and bottom. So this one would become a 12 over 20. And what would I need to do to the 7 over 10? Yeah, multiply by 2, and it would become a 14 over 20. Okay? So somehow we've got to get them in a way that we can compare them. Common denominators is a really nice way since we have more than 2 terms. And now you can compare. Which one's the smallest? Because it says ascending order, which means smallest to largest. So which number is the smallest? The 12 over 20. But 12 over 20 was the original fraction 3/5. And I'll use my less than sign to make sure that we are real clear that we're doing that in the right order. What number would come next?
13 over 20.
Yeah, 13 over 20, which was the way that it was originally given to us, right? And then, of course, the biggest one would be the 14 over 20, which was originally given to us as 7 over 10. That's a bad 10. Let's do that again. Okay. And we have our ordering complete. So when you're doing the ordering, you should be doing the ordering with the original fractions you were given, not whatever you've changed them to compare them well, okay? So let's do one now where we're just comparing 2 numbers instead of comparing 3 numbers. So on this one, where I'm comparing 2 numbers, it wants me to put the right symbol, greater than, equal to, or less than between the 2 fractions. Now, there's actually other things we could do on this one that don't even look a lot like what we've done before. You could probably look at these and just reason which one has to be bigger. Can you tell which one has to be bigger for sure? Sorry, it sounds like garbled on it. You have to be really loud for me. Yeah, the 51 over the 215 has to be bigger because the numerator's bigger, which is also great, and the denominator's smaller. In fact, that 51 over 215, it's almost like the number 1/4 because it's almost like having 50 over 200, right? So the second one is definitely bigger, and you can reason that out, and that's fine. I'd like to practice the other one that we just talked about, though, where we compare using our cross multiplication, okay? So we can compare by taking 21 times 215 and taking 51 times 430. So what is 21 times 215? 4,515. Mm-hmm. And what is 51 times 430?
21,930.
Yes, 21,930. Obviously, 21,000 is bigger than 4,000. And what that means is that way back up here, when I put that in there, the symbol had to be the same. I think it's worth noting, but I won't do it, that we could also get a common denominator here pretty easily. How would I go about getting a common denominator here? Yeah, the second fraction, the 51 and the 215, I could multiply each of those by 2, right? And then if the denominators are the same, I could just be left comparing the numerators. So that would be a third option. So unless it specifies how it wants you to do the problem, and I don't think it does on any of these, you can use whatever method that you'd like. But you have to actually use something. So if you wanted to justify it like I was talking through originally by saying sort of approximately, that's okay, but you need to write down some of your thinking so that we know where you're coming from on that too, okay? All right, there is a property called the denseness property for rational numbers. And it says the following. If you have any two rational numbers, a over b and c over d, there's always another rational number between them. So I suspect that you've had the opportunity at some point to play with a graphing calculator or your iPhone and zoom in and zoom out. Have you done that before? Yeah. And so you zoom in and you zoom out, and whatever space was there just gets magnified, right? So it happens on a calculator screen if you zoom in and zoom out. It happens on your computer screen. It happens on your phone. I mean, that's the whole point. Otherwise, why would we be zooming? We want to see it with the space bigger, right? And so that's actually what the denseness property says. There's always space between two numbers. No matter how close they are, you could always find some space between them. And if you imagine doing that from a zooming perspective, it happens here too. So like, you cannot hardly see any distance between there. But if I turn my screen around, which is zoomed in, you can see that there actually is some space there. It's practically indiscernible on your screen because it's so small for projection purposes. But on my screen, it's big enough to see. Okay? So if there's space between there, then there's some number between there. And there's many numbers between there, actually infinitely many numbers between there. There's a couple of different ways that you could find a number between there. One of them is by finding the midpoint. You've used midpoint formulas before. You add the two numbers together and divide by 2. That's an averaging feature. It finds the midpoint. But there's actually one that's friendlier for fractions. Really good. Because I'm telling you what, I don't really think you want to add 51 over 230 and 52 over 230 together and then divide by 2. Their numbers are just ugly. So this property, theorem 6.5 says that if you have the numbers a over b and c over d, and a over b is smaller than c over d, you can actually add just the numerators together and just the denominators together, which is not the same as adding fractions, right? That's not the same at all. We'll talk more about adding fractions and things later, but it is not the same. But you will still end up by doing so find a number that is between a over b and c over d. So taking a look at these numbers, which are by definition atrocious. I mean, those aren't fractions I want to do anything with. Are you going to do something with them? Not if you don't have to, right? I mean, I do not want to add these together because if I have to add fractions together, I have to get common denominators. How do I get common denominators between 427 and 92? I don't want to deal with those numbers. They're ugly. But the property that we just had before, Theorem 6.5, says that I can actually just add the numerators together, 33 and 7, and add the denominators together, 427 and 92, and I will have a fraction that is between them. So indeed, that will give me 40 on top, 519 on bottom. So you might be saying, well, okay, maybe it worked and maybe it didn't. How can I make sure she's right about that? Well, if you want to use your calculators to verify that, just conceptually that it made sense and it worked for yourself, you could turn each of these into decimals in your calculator, right? So you could find a decimal approximation for 33 over 427, and you could find a decimal approximation for 7 over 92, and then you could find one for the number we found, 40 over 519, and you will find that the decimal approximations put them in the order that we were intending for them to be put. It lies between them. Cool fact. Much friendlier than finding the midpoint between those two fractions. So why is it then true? I mean, we've said it's true. We found one. Why does there have to be a number between these fractions? I mean, this is a method for doing it, but why does there have to be a number between them? Because It's a property of real numbers, right? Property of rational numbers is true for real numbers as well. That there's always a number in between two rational numbers. That's why. There's always space. There's always, conceptually speaking, a midpoint between two numbers. So over here, where it asks us that, it's because rational numbers are dense. That doesn't mean dumb. Dense. I.e., it's Theorem 6.4. Space there, I think so. Theorem 6.4 proved it. There's always a partway point, a halfway point, an in-between point between two numbers. All right, so usually at the end of lessons, as you've had me before know that I kind of do this toward the end of my lessons, I like to throw in questions that seem like the section that's called, I call it section C, connections. Is that what your book calls it? Somebody help me out. Connections? Emily says yes. The connections section in your book. So the connections section in your book, there's a section A of homework problems, and then there's a section B of homework problems, and they look a lot alike. You know, problem number 1 here looks like problem number 1 here. And then the connections section of problems look more like the kinds of things that you might be faced with in a real classroom setting. Errors that students make, misconceptions that they have, questions that they might be asking you. So this is one such problem. A student simplifies the fraction m plus n over p plus n to m over p. So a few thoughts on this. First, what did the student do? They canceled out the plus n, you betcha. That is what they did. Okay? Why might they believe that this is a valid operation? Brooke?
Because when you're looking at it with just letters, you can't visualize like the adding, whereas if you use numbers like adding two numbers, so they might think, well, oh, there's n on top, n on bottom. Like just cross them out.
Yeah, and where do they see that when it is appropriate?
It's not addition.
If it's not addition, right, when it's multiplication. So they do have that feature available to them to sort of just mark things out, but not when it's addition, when it's multiplication. So for multiplication, this idea, we'll say it holds. And that's actually the fundamental law of fractions that we saw before, where it told us it works. So they're using sort of some information that they've learned in one context, and they're trying to extend it to another context, which we do all the time. But it simply doesn't extend in this particular context. So on part B, section, I have 2 B's. I have C on my screen. You have 2 B's. Do you have 2 B's? Awesome. It's good to know. Error to fix for later. Section, or part B, the second, how would you help the student? And so I'm going to piggyback off what Brooke said, because I think it's a really good idea. You mentioned the idea that because it's letters, it can be sort of confusing. But if there were numbers, you might see more quickly why it doesn't work. So I think a numerical example helps a lot here. And there's nothing special about the numerical example that I'm going to pick. I'm going to pick 2 plus 3. I should have left it the way it was. 2 plus 3 over 5 plus 3. So if the student did what they are thinking they would be able to do, right? If they did this, they'd get 2/3, right? 2/5. Sorry, wrong number. Thank you. 2/5. But what should they be getting? Yeah, they should be getting 5 over 8, right? Because they really should be adding the top together, adding the bottom together, and then seeing what they come up with. On these particular ones, you might then say, well, how do you know the 2/5 are not equal to 5 over 8? So we've done several problems talking about how we decide if fractions are equal. You can cross multiply, you can get the same denominator. On this particular one, they actually are both in simplest form. 2 over 5 and 5 over 8, neither of those simplify. And if they're in simplest form and they're not the same, then they're not equal. And so we can know it from that perspective as well. So numerical examples are very, very helpful for students. So let's try another one. This one's kind of just a fun visual imagery of what's going on. If we were to take this set of numbers equivalent to 1/3, okay, so a set of numbers equivalent to fractions that are like 1/3. So like we took 1/3 and we did 2 over 6, we made equivalent fractions, and we did like 3 over 9, okay, equivalent fractions. And we let the numerator be the x and the denominator be the y, what graph would we get? So in other words, they're saying 1 over 3 becomes 1, 3. 2 over 6 becomes 2, 6. And 3 over 9 becomes 3, 9. So pretty good so far. Yeah? Okay, so what I'm going to do is I'm actually going to switch to the next screen because I think I have a grid. I do. And we're going to plot them. So you can plot yours on your paper along with me. I'm going to plot mine here. We had 1, 3. We have 2, 6, and 3, 9. Do that. What kind of graph is this going to create? I mean, I just picked 3 very specific values, but there's infinitely many values I could pick. What's it going to be? Somebody give me a guess. It's going to look like a line, right? Connect the dots, like the Chili's menu for the children, right? Yeah, let's connect the dots. It's going to look like a line. Now, there is a caveat to this line that may not be sort of obvious right at the get-go. Looks something like that. Connect the dot to get a line. Every point along that line has that ratio where the x is 1/3 of the y, right? Like everyone does, except for one point. Do you see a point that causes problems with that description? Yeah, the one that goes through the origin. This particular ordered pair, and it's the only one, does not fit the description. So what you actually really get is like an open circle there. You've seen open circle graphs before. You get an open circle there. So what is this actually if we were to sort of describe it? Well, it's a line, like y'all said. It actually has a slope of what? Can you tell? Three? Yep, slope of 3. Line with slope 3. But not including or does not include the origin. And I'll just put including 0, 0. So you get this very interesting sort of an image when you create equivalent fractions. And there's nothing special about 1/3. It would work if I did 2/5. I wouldn't get a slope of 3, but I'd still get something that's a line where I might have to omit something if it doesn't fall within the correct values of what's going on. Any questions on that? All right.